Things first, oscillator. Basic definition of an oscillator is
generate a waveform at a nearly constant amplitude and frequency.
what? Gosh! Definition.
Generate a waveform at a nearly constant amplitude at a given frequency.
You sound like Gordon. Yeah, I know wave. Must be thinking about Kate Moss or something. Waveform. Not forgot already, Goss.
At a nearly constant amplitude at a given frequency.
Why is that fun? I don't need it. That's so. Specified is probably a better word. Frequency, because you have to basically like select it, right? No. You have to determine the frequency. It's not like one of the blocks. What's the first block called? Oscillator. Frequency determining network. You need to know these things. Frequency determining network. Okay, so we got a frequency, we got picked out. How do we keep that thing here, nearly constant? The size of it, what we got to do? Yeah, regenerative feedback. We probably want to have some kind of amplification going on. So we have amplifier switching network. And we got to feed it back into itself using what kind?
Generative feedback.
Using positive or regenerative feedback. Because that prevents what? Yeah, because this is what I want. This is what can happen if something breaks. So I can keep this by using positive or regenerative feedback. Because this right here is called signal what? Signal dampening. I don't want that. So I can basically take a DC circuit and generate an AC waveform? Yes. I like them apples. All right. Frequency determining network. There were some examples we talked about. The first one was this LC tank called what? I can use an LC tank. What do we call it?
Flywheel effect?
Yeah, it's a flywheel effect. Because I can place an inductor capacitor in parallel with each other, and ultimately, what are they doing? It's kind of like struggling, and eventually they'll oscillate at resonant frequency, and I can use that as an example to determine the frequency. I'll put that in my circuit. Okay, I'll use this LC tank circuit. Okay, that's cool. But there's one that's better. Yeah, better than this, or this one was, what was this one called? This example right here. Because this also is part of a frequency determinant network, or a method or a circuit that can be used. What do we call it? Or what's it called?
RC network.
And it's called RC feedback, right? Network or something like that? Huh? RC feedback? Sometimes, loosely, it can be referred to as a phase shift oscillator. Loosely. And each little network here, if you will, 60 degrees, 60 degrees, 60 degrees, it's going to phase shift. Have an op amp feed it back into itself. And since it's my inverting input, 180 degrees out, but it's going to just keep feeding back into itself. So this is another example. But over time, with this and this, what could happen to the components over time?
Degrade.
They can degrade or deteriorate. So over time, I'll write in a different color, orange, over time, components, what did you say? Okay. Degrade, because we already have to deal with tolerance issues, don't we? So, yeah, we already got to deal with that. So for this one specifically, related to this, what I just wrote, over time and components degrade. So what can we do here to kind of like, yeah. So here in the third stage, we can add either a variable resistor or a variable capacitor to kind of tweak it back in, because key word here, drift, in this occur. So, hey, we can tweak it back in if we need to. So that could be the beauty of this one if you decided to use this. But hey, this is like the 21st century stuff. Even before the 21st century, what's better than these two as far as this goes? Using crystal, quartz, crystal, Xtal, crystal. You have to identify the symbol of a crystal. It's an ice cream sandwich. It might. It will. How do we know if we want to use a crystal, what frequency we're going to try to sustain? No.
Size and cut.
Yeah, it's the size and cut right here. The size and cut of the crystal is what actually determines the frequency. What can I do to make that thing vibrate? Squeeze the crap out of it! Known as the... This is applying external pressure, really, whether it be mechanical, electrical, applying external pressure. External pressure. And by doing so, you can cause that crystal, quartz specifically, I know it wrote up here somewhere, yeah, to vibrate or oscillate at its resonant frequency.